Hello, I've got a lab that I would like to discuss with you and have you work out how you understand it and some calculations. So here's my apparatus. I've suspended this quite a bit above the ground because I have a pulley here, and this pulley operates very smoothly on bearings. It will spin for quite a long time. And I've shown you before that the wheels of this cart also will spin for quite a long time on bearings. So this is not a friction-free pulley because there is no such thing, but it's as close as we can get. So I have a string connected to this cart going around the pulley, and at the bottom of the string I have this connected to a small mass. I also have a photo gate here which will track the acceleration of this cart as it goes through the photo gate using this picket fence timer. In addition to that, I have a mass back here. It's technically a magnet, but this ramp is aluminum, and so it has no magnetic effect whatsoever on this. And this mass, this bar here, has felt on one side. But also, I can place it up here so that I have three different things I can do with this. I can let the mass, the force of gravity on that mass, pull this cart so that it accelerates. I can also do that with this dragging behind with felt as the interface of the surface, so that it has relatively low friction on the track. And when I do this, it will still accelerate, but at a somewhat lower pace. And lastly, I can do this without the felt, so that there's a little bit more friction going on there. And if I let the mass pull the cart now, it still moves, but it is definitely at a lower rate. So I'm going to take some measurements here, and then we will begin conducting the lab. So before I take any measurements of acceleration, I need to take measurements of mass. So this is the mass that falls. And I have a mass here of 78.5 grams. So it's 78.6 grams. We'll go with 78.6, I guess, because it seems to be holding steady there. Okay. I also would like to take the mass of the car and the bar that drags behind it independently. So here is the bar that drags behind it. Mass of 158.7. 8, 7. Well, you can decide if you want to use 7 or 8 or 7.5. So that's the mass of the bar. And then I have the mass of the car, but I don't want to forget that when this mass falls, there is some mass taken up in this string. And I know it seems like nothing, but let's see. We've got 295.3. 0.3. If I add the mass of the string, I get 296 grams. Oh, 295.9. There was some mass to the string, so this is my mass of the cart and the string, independent from the mass of the bar and independent of the mass of the falling weight. Before I begin the experiment, in order to make sure that this cart is level, I'm going to do two different things. I'm going to use this little level, and I recognize that this little level is not necessarily the most accurate because it's so short that it really only measures the levelness of a track in a very finite area. It looks to be level everywhere. And the other thing I'm going to do is measure the distance from the table to the height of the ramp on the side opposite the support. So I've got, looks to me like 76 centimeters, almost exactly right there. And I think it's the same here. So we do seem to have a level cart. Okay, so now I'm going to set up the Smart Gate with, this is called SparkView, and you have the same program on your Chromebooks. So try to pay attention to this because if you're lucky enough that we can do some labs in class, you'll be using this when you're connecting to sensors. So I want to go to sensor data, and in sensor data I see Smart Gate because that's what I have set up here. And so I'm going to press this little, click on this little gear right here, and I have a few different options. These gates have an auxiliary port, but we're not using that auxiliary port. So we're not going to use the auxiliary port, we're doing Smart Gate only. And I'm doing a Smart Gate and picket fence. So I'll click that and OK. And it wants to ask the flag spacing. So I've measured these small ones here. They are 5 millimeters apart, which is 0.5 centimeters, which is 0.005 meters. So it gives you as a default 0.05 meters, which would be 1 centimeter, but I want half a centimeter. So I want to add an extra 0 in there and say OK. And it gives me the choice. Do I want to measure position, velocity, or acceleration? And for this experiment, I'm going to measure acceleration. And then it wants to know if I would like graph or table, graph or table and graph, or just numbers. And I'm going to go with just numbers for this experiment. And so when I'm ready, I will hit the start button here and we will get started. I'm going to place a weight in front of this to try to hold it there for a second while I steady this. I'd like you to notice that the string is not dragging on the bottom of this block, so there is not friction coming from there. If there is friction in the system, it is coming from the bearings here, or the friction of the string interfacing the pulley, or from the bearings in this cart. And obviously there is friction from the mass bar with the felt drag. Okay, so I'm going to do 4 runs of each of these to get averages. So I'm going to pull this back. I want it to start on the far side of the photo gate, and I'm going to go ahead and hit start, and I want that to turn into a red square. And I'm going to pull this back until the mass is just below the pulley. Now this is pretty high and I don't want the car to crash. So I'm going to let it go, and I'm going to go ahead and let it crash into the barrier at the end, but I'm going to be ready to catch it too. So here we go. Alright, so I got 1.39 meters per second squared for the first run. Alright, so we're going to do this again. So second run. That time I got 1.65 meters per second squared. Okay, third run here. The mass on top of the cart. You got 1.46 meters per second squared. Okay, and now for my fourth and final run with the mass bar on top. Make sure I start this. Okay. 1.3 meters per second squared. So now I'm going to run 4 trials with the cart with the felt dragging behind. So I'll move this off the cart. So we have the same mass here between the two of them, but now part of the mass is dragging as opposed to all of it riding on top of the cart. Oops. And I will start it. And I have 0.78 meters per second squared for the first run with the felt dragging behind. 0.78 meters per second squared. Trial 2. .31 meters per second squared. Seems to be very different. .70 meters per second squared. This is the fourth trial run with the felt dragging behind. .89 meters per second squared. And now we were going to do 4 trials, but this time instead of having the felt dragging, I'm going to have the non-felt side dragging. So now I'm going to do 4 runs with the bar dragging behind, but the felt is not contacting the track, just the metal of the bar is contacting the track. .56 meters per second squared. Forgot to stop that before. .52 meters per second squared. Okay, trial 3. .56 meters per second squared. Last run. .59 meters per second squared. So these are the accelerations for 4 different runs of 3 different scenarios. One is with the cart with the mass on top. Another is with the cart with the felt dragging behind. And so what I mean by that is this mass bar with the felt on the bottom is dragging behind the cart as it accelerates. And the last is the cart with the metal bar dragging behind but no felt. So that's like this. Now that I'm done with this, I'm relatively comfortable with the consistency of this column and this column, and with most of this column with the exception of this number. This seems like a significant outlier to me relative to these other 3 numbers. So I'm going to do one more run with the felt dragging behind and see if I get something more consistent and possibly replace this number. And I have 0.74 meters per second squared. So having replaced that data point, I now have relatively consistent results in all 3 columns. And I'm happy with this and ready to begin calculating.